Good afternoon, class. Today I want to discuss the fundamental theorem of calculus, and I figure it's got to be important with the name the fundamental theorem of calculus. Let's suppose we had the graph of a function y equals f of x, and for the sake of this illustration, we'll assume that it's in the portion I'm looking at is in the first quadrant. And let's suppose we're looking over an interval from A to B. If I wanted to know the area bounded by the graph of y equals f of x, the x-axis, and the vertical lines x equals A to x equals B. That's this area right out here. I want to know that shaded area. Oh, we know area formulas for rectangles. We know how to find the area of a triangle, circles, what have you. But what about such an irregular shape? That's what I've drawn right here. What we could do is imagine little bitty rectangles inside this area. And we could go through using base times height. Realize the height is given by the y coordinate on the green curve. This area, I'll say the shaded area, can be found using something called a definite integral. Remember, an indefinite integral is just an antiderivative. We've seen that. But this is a definite integral. The x values are ranging over the interval from A to B. So the height is given from the x-axis to the green curve. The height is given by the y values on that green curve. So the height, we'll say, is given by f of x, and that base length, imagine millions of tiny little rectangles that we use in base times height to indicate the change in x, that horizontal distance, that base length, that's dx. The f of x gives us the height, and the dx we could think of as the base length. Suppose we have a function. Let's see, I'm going to draw another graph real quickly. Let's suppose we have the graph of y equals f of x on top. And suppose we had a lower function. I'll call that y equals g of x. And once again, we want to know, I'll say there's A, and right there's B. We want to know the region bounded between y equals f of x, the area of the region bounded by y equals f of x, y equals g of x, the vertical line x equals A, and the vertical line x equals B. I'm pretty sure I don't have a formula, a geometric formula, for determining the area of such an unusual shape. Well, using the definite integral, that shaded area can be expressed. Once again, the interval is from A to B. Now, the height of this area, it's given by the top function minus the bottom function. You're determining that height between the two curves, so that would be given by f of x minus g of x. Up here, the height was just f of x basically minus 0, Here it was just f of x minus 0. But if you're interested in an area that's not bounded by the x-axis, but by some other function, you subtract the functions, and that base width is still given by dx. So my question is, how do we evaluate a difference quotient? Not a difference quotient, pardon me, a definite integral. How do we evaluate a definite integral? We have something called the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus says that let's assume that you have a antiderivative for some generic function f of x. I'm going to say, let's assume capital F of x is an antiderivative of little f of x. I make a note, I said it's an antiderivative. It can be any antiderivative. So I'm going to make a note here. I'm always going to use the antiderivative where that constant is 0, so we don't have to keep adding on that plus c and then each time. So I'm going to make a note here saying use the antiderivative with the c equal to 0. Then the definite integral from a to b of f of x dx is equal to the antiderivative evaluated at b, the upper limit, minus the antiderivative evaluated at a. In general, if you have an antiderivative with a plus c here, then when you subtract that constant of integration off. That's why we don't need that plus c. But what you need to see is a definition, an example, because this is not that bad. You've made it through the worst, finding all those antiderivatives using the various techniques of integration. So, okay, number 1. Let me write this down. We want the definite integral from 0 to 4 of, I'm writing down the problem, 5x squared minus 4x plus 8 dx. The first thing you need to do is anti-differentiate this function here. Well, we know how to anti-differentiate this. This is just a polynomial function. So let's anti-differentiate 5x squared minus 4x plus 8. We know in that event we're going to be adding 1 to the exponent and dividing by the new exponent, as we've seen in previous homework assignments. So that 5x squared, that becomes a 5x cubed divided by 3 minus that 4x, make it a 4x squared divided by 2 plus, what's the antiderivative of 8? No, it's not 0. You're thinking derivative. How about 8x? I agree. The antiderivative of a constant is just the constant times x. And normally I'd write on that plus c, but I don't need to, okay? I can use any antiderivative I want to, so I'm going to use the one that has the constant of 0. So we can clean this up. That's 5x cubed over 3. 4 divided by 2 is a 2x squared plus an 8x. Now, our final answer is going to be a number. Realize that. We're looking basically at the area that's bound by the curve. Now suppose the function is under the x-axis. Well, you may wind up with this thing being negative. Well, area can't be negative. We'd have to modify that. So it is possible for definite integrals to be negative, but you still go, you take 5x cubed over 3 minus 2x squared plus 8x, and I'm introducing some new terminal notation. That little squiggly there, the integral symbol, I'm going to replace it with a vertical bar from 0 to 4. This notation is saying, go through, plug in 4 for everything. I'm evaluating the antiderivative at the b value, so I'm plugging in a 4. That's 5 times 4 cubed minus 3 minus 2 times 4 squared plus 8 times 4. So all of that is what I get when I plug in the 4. And then minus. We evaluated the antiderivative at b. Now minus, evaluate the antiderivative at a. Well, I think I'll go ahead and write this down, but I bet y'all can tell me what's about to happen when I plug in all those zeros. We'll have 5 times 0 cubed over 3 minus 2 times 0 squared plus 8 times 0. There's the minus. Before we go on, can look at that second set of parentheses. What is that going to give me? I agree, 0. We're going to get 0 there. Notice everything's being multiplied, every term is being multiplied by 0, so the minus part is just a 0. What about all of this here? We'll dig out our calculators. That's 5 times 4 cubed, and then we have to divide that by 3, minus 2 times 4 squared plus 8 times 4. Let's see, let's convert that to a fraction. If you're using a type of calculator, we know that that 0.666 is 2/3, but if you're using this type of calculator, which I think most of y'all are, the easy way to do it on your calculator is to go math, convert to fractions, so math enter 320/3. 320/3 minus 0 gives us a final answer of 320/3. If you know how to find the antiderivative, then the definite integral part is easy. You plug in that upper number, minus, plug in that lower number. So my final answer, coming back over here, I'm getting a final answer of 320/3. Any questions there? Now, if this were a scientific-based calculus class, we would spend so much time on definite integrals. That's where most calculus classes really take off. It's this anti-differentiation and definite integrals. But for us, this is about the end of the course. So number 2, let me write this problem down. We want the definite integral from 1 to 9 of 35y times the square root of y plus 15 times the square root of y dy. And make sure I didn't miscopy this. Okay. The first thing we have to do is anti-differentiate 35y square root of y plus 15 square root of y in terms of y. So the first thing, we're going to antidifferentiate this. And we know ever since, well, I guess we started it with a differentiation. When you run into a y, you rewrite that using what when you run into a square root, you rewrite that using what exponent? The square root of y is the same thing as? Correct, y to the 1/2. So we have another 15 y to the 1/2 dy. And y times y to the 1/2, that's y to the first times y to the 1/2. Repeated basis being multiplied, what do you do to the powers? Okay, you add them. 1 plus half is 1.5. We'll write that as y to the 3/2, 1/2 plus 1. That's still a 15 y to the 1/2. Well, I'm running out of room. I should have just come down here. But I think we're ready to okay, wait. Y to the first times y to the 1/2. Did y'all hear that question? What did I do here? Repeated basis being multiplied, so I add the powers. 1 plus 1/2 is 1.5, and 1.5 is the same thing as the improper fraction 3/2. So we have 35y, you add 1, 3/2 plus 1, that's 3/2 plus 2/2, that's 5/2, and then you divide by 5/2. We'll have to simplify that in a moment, plus you have a 15y, 1/2 plus 1, that's 1/2 plus 2/2, which is 3/2, divide by, what are we going to divide by? 3/2, I agree. And once again, I'm not going to add on the plus c, because with the fundamental theorem of calculus, I get to choose the antiderivative I use, and I'm going to use the one that has a constant of 0. And a compound fraction, I multiply above and below by the minor denominator 2. Here I multiply above and below by 2 again. So we have 2 times 35, that's 70 y to the 5/2 all over. What are we left with there? 5, I agree, plus 2 times 15, that's 30 y to the 3/2 over. The 2's cancel. What are we left with? 3. And this is going to reduce pretty nicely. Let's see, 70 divided by 5. I think that goes in evenly. Isn't that 14? Y to the 5/2 plus 30 divided by 3. That's 10. Y to the 1/2. And now we want to evaluate this on the interval from 1 to 9. So we have 14 y to the 5/2 plus 10 y to the 1/2. We're going to evaluate it on the interval from 1 to 9. That means we have to go through plugging in 9 for both of those y's, minus, then we go through plugging in what? 1. This is where we're using the fundamental theorem of calculus. Evaluate the antiderivative at the top limit. I'll just say the top number. Evaluate the antiderivative at the top number minus evaluate the antiderivative at the bottom number. So we are going to go through. First of all, we'll plug in 9. So that's 14 times 9 to the 5/2 plus 10 times 9 to the 1/2 minus, go through plugging in 1. That's 14 times 1 to the 5/2 plus 10 times 1 to the 1/2. Do you remember how these fractional exponents work? That 2 says you take the square root of 9. The square root of 9 is 3. And then 3 to the 5th is 243. So we have 14. Oh, I think I'm going to need my calculator. Let me pull up my calculator for this. Yeah, that's what y'all would do? Okay, then that's what I'll do also. I'm going to pull up my calculator. So I'm first of all looking at the 14 times y raised to the. Now, if you're going to punch in that 5/2 exponent, if you're punching in that 5/2 exponent, you better enclose that 5 divided by 2 in parentheses. Otherwise, you're just going to be raising 9 to the 5th power, and that'll give you a huge number, and divide the result by 2. Or, okay, you're right. Or we could have punched in a decimal value for 5/2. That's 2.5. We could have done that also. Plus 10 times 9 raised to the. Do you want me to just put in 0.5 for the 1/2 instead of 1 divided by 2? Yes, just punch in the 0.5. So all of that stuff is this first set of parentheses here. Enter. That's giving me 3,432 minus. Now I'm going to do this second set of parentheses. Left parentheses, 14 times, what? Oh, this is nice. Hadn't even thought about this. 1 to any power is, 1 to any power is still 1. I agree. So that's 14 times 1 plus 10 times 1 to any power. The square root of 1 is still 1. I don't need a calculator for this one. I can do this one in my head. 14 plus 10 gives me 24. So we have 3432 minus 24, which gives me a 3,408 for my final answer. Oh, y'all want to see the, okay. Someone asked me to show what I was doing right here on the calculator. Okay. 14 times 1 to the 5 divided by 2 plus 10 times 1 to the 0.5. My mental arithmetic said it was 14 plus 1, which is 24. I sure hope that's what the calculator gives me. Otherwise, that'd be sort of embarrassing. Yep, sure enough, there it is. 24. Any questions there? As soon as you find the antiderivative, the rest is just number crunching. Plug in the 9 minus plug in the 1. So you have our final answer, 3,408. Oh, let me look. Did y'all catch my mistake? Let me see. Let me look for my mistake. Let me first. Okay, I see what someone was out there in the audience. The look y'all have been giving me. How many of y'all watching this spotted the mistake? My mistake. 70 divided by 5 is 14. Okay. Y to the 5/2. 30 divided by 3 is 10. Y to the, what should that exponent have been? Oh, wait, I did switch over. Y'all don't be ashamed to call out if you spot a mistake. Even if I'm recording, I'd prefer that. What did I do? That should have been a 3/2. What did I write? 1/2. That should have been a 3/2 and a 3/2. So that should have been a 3/2. One thing's for sure, at least, that second set of parentheses will stay a 24. But I think this first one's going to be different. Go back to your calculator. Punching in this first portion, this first set of parentheses. 14 times 9 raised to the 5/2 plus 10 times 9 raised to the, what was that exponent? 3/2. That was where I made my mistake. 3/2 equals 3672. This should have been a 3672 minus, what's that, 3672? Yes, minus 24. Should have given me a 3648. It's a good thing we have 3 chances to type in the correct answer. Y'all agree with that? I see y'all out there punching in your calculators. My lab agrees with it. Any questions there? And now don't be scared to call out. This late in the semester, y'all should know not to be scared to call out when you spot me making a mistake up here, okay? Any questions there? Let's do another one. Let me write it down. Number 3, we want the definite integral from 1 to 3 of 8n to the negative 1 plus n to the negative 4 dn. Okay, let me make sure I have it copied down correctly. 8n to the negative 1. Okay, yes. Okay, first thing we have to do is anti-differentiate. Let's find the antiderivative of 8n to the negative 1 plus n to the negative 4 dn. Oh, I like this. What do we have to do here? Well, we know what to do here. With that n to the negative 4, we add 1. That gives us an n to the negative 3, and we divide by negative 3. What are we going to do here? If you add 1, what are you about to get? A 0? Can you divide by 0? No, remember you have to, that's right. Okay, I heard it. It's 8 over n dn. And we know the antiderivative of 1 over n dn is the natural log. That's the natural log of the absolute value of n. The 8 is the coefficient of ln absolute value n. Do I remember that? Antiderivative of 1 over n. I'll say the antiderivative of 1 over n dn is the natural log of the absolute value of n plus c. If there's a constant like an 8, then the 8 goes in front. So now we have to evaluate. We have 8 ln absolute value of n plus a negative. I'm going to write that as a minus n to the negative 3 over 3. We're evaluating from 1 to 3. So we go through, plugging in the 3, 8 ln, the absolute value of 3 is just 3, minus 3 to the negative 3, 3 to the negative 3, divided by 3. So that's what we're getting from plugging in the 3, minus, now we're going to go through plugging in the 1. So we have 8 times the natural log of 1. Oh, I like that. I know what the natural log of 1 is. Minus 1 to the negative 3 all over 3. I know what that 1 to the negative 3 is. 1 to anything is 1. So we really have 8 ln 1 minus 1/3. Let me look here. Do they want the answer in terms of natural log? Oh, wait a minute. Round to 4 decimal places. So we're going to have to use our calculator and get a decimal approximation. 4 decimal places. 8 ln 3. Remember, if your calculator opens a parentheses, when you press that ln, you have to close the parentheses, minus 3 raised to the negative 3 divided by 3. Okay. And we have that big long thing there, 8.77, what have you. I'm not going to round until the very final answer, so I'll say minus. Now I'm going to punch in the stuff on the second set of parentheses. 8 ln 1. Why did I say that was nice? What's the natural log of 1? 0. I agree. So 8 times 0, that's 0. Minus, oh, wait a minute. Oh, my Lord. It just now dawned on me. I hadn't shown you. I mean, I still hadn't switched over to my paper. So we went through all that anti-differentiation. And I'm evaluating from 1 to 3. And I'm plugging in. Remember, I switched a moment ago to see how do they want it punched in. I didn't switch back. So you can't see what I'm punching in, can you? Let me start all over then. Now you can see, here's what I'm punching in. Left parentheses, 8 ln 3, close parentheses, minus 3 raised to the negative 3 divided by 3, right parentheses. I'm just going to punch it all in as one thing. Minus, that minus I just punched in is this minus right here. Left parentheses, 8 ln 1, close parentheses, minus 1 to any power is 1. So I'm just going to say minus 1 divided by 3 equals, they want it rounded to 4 decimal places, so I'm getting a 9.10. Look at that. That's a 988. So what's going to happen to that 8? Is it going to stay the same or is it going to go up? It's going to go up. So 9.1099. 9.1099. Any questions there? Now be honest, how many of y'all would have tried to add 1 and then divide by 0? That should have set off the warning bells that you're doing something wrong. Remember, that power rule does not apply to anti-differentiating a variable to the -1 power. That's where the natural logarithm comes in. Any questions? Let's see, I was going to do 5 problems. Here's the next one. Oh, I know how much y'all love those square roots. Let me write this one down. This is number 4. The definite integral from 0 to 3 of 3 times the square root of 8x plus 1 dx. Let me make sure I don't miscopy it. Well, we know how to anti-differentiate square roots. We're going to anti-differentiate this function. Once we find the antiderivative, we'll plug in 3 minus, we'll plug in 0. Well, if we're going to anti-differentiate this, we know that a square root is the same thing as the exponent of 1/2. So we have 3 times 8x plus 1 to the 1/2 in terms of x. We're going to have to use one of those techniques of anti-differentiation that we saw earlier. If we have a quantity raised to power, I would use a U-substitution. I'd let U equal the thing that's being raised to the power, 8x plus 1, and then du is equal to 8. The derivative of 8x is 8. The derivative of 1 is 0 times dx. So we're going to be replacing this thing, the 8x plus 1, that'll be a u. The only other thing we have with the variable is that differential of x, but we don't have an 8, do we? So divide. Also, I think I normally multiply by 1/8. That's what I've been doing in my other videos. So I just have 1/8 times du is equal to dx. So I'm going to replace the dx with the 1/8 and the du. Excuse me. Any questions there? This is standard U-substitution stuff like I've done in my other videos. The quantity raised to power, I try letting u equal. Find the differential. I didn't have an 8, I had just the dx. So I solved for dx by multiplying both sides by 1/8. And then I replaced the dx with 1/8 in front and the du at the back. Let's clean this up. 1/8 times 3. That's 3/8. So I'll write the 3/8 times the indefinite integral of u to the 1/2 du. Three times 1/8 became 3/8. We have a u to the 1/2 du, and we know how to anti-differentiate u to a power. As long as it isn't -1, you add 1 to the exponent. 1/2 plus 2/2 gives us 3/2. Divide by 3/2. Oh, this is working out nicely. We know multiplying fractions, you multiply the numerator. 3 times u, that's just a 3u to the 3/2. This thing is working out nicely. 8 times 3 is 24. Divided by 2, what are we getting? Or you could go 2 goes into 8 4 times. Whether you go 24 divided by 2, or if you cancel first, 4 times 3, you're still getting what in the denominator? A 12, I agree. And we could cancel a 3 above and below to get u to the 3/2 all divided by 12 divided by 3 gives me a new denominator of 4. But before we make the substitutions, 0 and 3 are in terms of x. Get the antiderivative back in terms of the original variable. So we have replaced the u. What do we have? What was u replacing? 8x plus 1. So we have an 8x plus 1 to the 3/2 all over 4. We replaced the u with 8x plus 1 to the 3/2 all over 4. We now have to evaluate at 3 and then 0. The endpoints of the interval, the limits of integration, 3 and 0. Plugging in a 3, I'm going to get 8 times 3 is 24 plus 1. That's 25 to the 3/2 all over 4 minus. Plug in 0. 8 times 0 is 0 plus 1, so that's just a 1 to the 3/2 all over 4. I can do this one without my calculator, I think. That little 2 says you're taking the square root of 25. We know what the square root of 25 is. The square root of 25 is 5. Cubed is 125, so we have 125/4 minus 1 to any power is 1. 125 minus 1, that gives me 124/4, which goes in very nicely 31 times. So, let me see if I'm going to move this up there so we can see the whole problem. Any questions there? Maybe I should punch in that 31 and make sure the way I've been doing today, I better make sure that's right. Any questions there? We anti-differentiated using a U-substitution. This stuff here, all of that is old stuff. That stuff we'd already done, anti-differentiating. The new stuff is the way we plugged in the 3 in the antiderivative minus the 0 in the antiderivative. Any questions there? Okay, I think there's another one. I'm just going to do 5 problems. Okay, number 5. Okay, let me write the problem down. It's another definite integral from 1 to 3 of 6 over 2x minus 1 to the 4th power dx. Let me make sure I didn't miscopy it. Yeah, that looks right. Oh, and notice they want it to 4 decimal places. Let me write that down right now. So 4 decimal places. So I'll remember And we're punching in our answer how we want it. Oh, wrong thing. First thing we have to do is just find the antiderivative. The antiderivative of 6 over 2x minus 1 to the 4th power dx. As I've said in previous videos, we do not have a quotient antiderivative rule. What we need to do, we can rewrite that as a product. That's 6 times 2x minus 1. What do we do to that exponent? That's right, make it negative. And then we have a quantity raised to a power. We're going to have to use one of those other techniques of integration. This is the same one we just used, the U-substitution technique. Let U equal the quantity raised to a power, 2x minus 1, and then du is equal to, the derivative of 2x minus 1 is 2 times dx. So we want 2x minus 1, that's going to become a u, so u to the negative 4 power. Hey, look at this. We have a 6 dx. We have a 6 dx. Down here we have a 2 dx. I think I could multiply and pick up and get even rid of that 6 there. What would I need to do? Maybe multiply down here by 3. So we have 3 du is equal to 3 times 2 is 6 dx. Did y'all follow my logic there? In the previous one, we couldn't do that easily because, let's see, we had a 3 and we had an 8 there. What do you multiply to change that 8 to a 3? That wouldn't have been so easy as this one. We have a 2. What do we multiply to change it to a 6? A 3. So we're going to, let's see, I'm going to replace the 6 dx with the 3. Where does the 3 go? In front, that's right. And the du goes at the back. Gosh, that's messy. So we have a 3 in front of the integral symbol. The 6 is gone. We have a u to the negative 4 du. Any questions over this? The antiderivative part is the most rigorous part. We're not through yet, but we're almost through. Now that we've made the substitution, we know how to anti-differentiate a variable to a power. We have a 3 u, add 1, negative 4 plus 1 gives me a negative 3, divide by negative 3. Oh, we can cancel a 3 above and below. So we have a u to the negative 3 divided by a negative 1. That negative. So we really just have a negative u to the negative 3. We're ready to plug in the 3 and the 1, but before we do that, the original function is in terms of x. That means these limits of integration are in terms of x. We have to switch it back in terms of x. So we have a negative. U was what? 2x minus 1. So we have that negative. We have the 2x minus 1. We have that exponent of negative 3. And we're going to evaluate this from 1 to 3, so 3's on top, 1's on bottom. I added 1, negative 4 plus 1 gave me a negative 3. I divided by negative 3. 3 divided by negative 3 gave me a coefficient of negative 1, u to the negative 3. Then I had to replace the u with 2x minus 1. Remember, u was taking the place of 2x minus 1. And now it's a matter of going through, plug in 3, plug in 1. So we have a negative. Plugging in the 3. 2 times 3 is 6 minus 1. That's the negative of 5 to the negative 3. Minus, this minus is from the Fundamental Theorem of Calculus. Then we have that black minus. Plug in 1. 2 times 1 is 2. Minus 1 is 1 to the negative 3. And they want it rounded to 4 decimal places. Otherwise, I wouldn't. I'd convert that to 1 over 125 and make it negative. But since they want it rounded to 4 decimal places, I'm going to punch this into my calculator. But that minus and negative, what's that going to become? What? It's going to become a positive. I agree. So here goes. Where's my calculator? Where's my calculator? I'm going to move that calculator closer to where I'm sitting so I can see it better. We have a negative, left parentheses 5, right parentheses, raised to the negative 3 plus 1 raised to the negative 3, but we know 1 raised to any power is still 1, but I'm getting the decimal 0.992. I want it rounded to 4 decimal places, but this thing appears to terminate after 3 decimal places. So we come back over here and we punch in a 0.992. Let's switch back to what we were doing. Any questions? Wow, this looks messy now. Sorry about that. We anti-differentiated 6 over 2x minus 1 to the 4th power. To do that, we had to rewrite it using a negative exponent. And then the quantity raised to a power, we used a U-substitution, the thing being raised to the power. We were able to get rid of the 6 dx by replacing it with a 3 du. The 3 goes out front, the du goes at the end. To anti-differentiate a variable to a negative 4, you add 1 and divide by the new exponent. We could cancel the 3's, just get a negative 1 u to the negative 3, substitute back in terms of x. Now all of this stuff here, none of that is new. All of that stuff is stuff we'd already done. The only new stuff in this assignment, the way we plug in that 3 minus plug in that lower number 1. Any questions there? Well, okay, then I'm going to stop this video. Hold on.